Okay, Paul, go ahead.
Cool. Well, thanks everybody for tuning in. This is joint work with Nelly Ung, who just moved to NTU Singapore to start her own group, and Henrik Wilming. And the central quantity of this work is the variance of relative surprisal, which is also known as the var entropy, information variance, or relative variance, which is how I'm going to be referring to it in those 4 minutes here. It's defined like this. So S rho sigma here is just the relative entropy for given rho and sigma. And then the relative variance is essentially the variance of this relative surprisal operator here around the relative entropy. And the take-home message of our work is the following. The relative variance is a useful quantifier of single-shot effects in the study of possible state transitions in a resource theoretic setting. It provides simple to evaluate conditions for a single-shot state transition to be possible, and in certain settings also has a resource theoretic interpretation. These conditions complement and can be related to known measures of single-shot effects, such as min and max relative entropies, and the conditions also have several applications. So that's all a bit abstract. I'm going to try and sort of give you a gist of the kind of results that you might be expecting in this paper in the remaining 2 minutes. So a bit of notation, which I hope is familiar to most of you. I'm going to be writing this relation here. So rho and rho prime is 2 quantum states stand in this relation. If there exists a quantum channel E that maps this lower index sigma, which is a fixed reference state, a kind of free state in a resource theoretic setting to itself. And if it takes the initial state epsilon close to the final state in trace distance. And so given this notation, it's well known that the relative entropy characterizes the IID as asymptotics for this, in the sense that if and only if this quantity decreases strictly, then for any epsilon, I can move from an initial tensor product state to a final one for sufficiently large n. And so the first result that I'm presenting here is that we essentially map this to a single shot setting where I again have this decrease of relative entropy, but I now have a corrective term, a function f, that depends only on the relative variances of the initial and final states and my smoothing parameter. And this condition is sufficient for the existence of the state transition in a single shot setting. This function is 0 or small whenever the first 2 arguments are small, showing that states with small variance and transitions between them essentially are already governed by the relative entropy at the single shot level. A kind of complementary type of result that we have in the paper is a necessary single shot condition, all of these in the semi-classical setting. So whenever I am able to implement a transition exactly using such a sigma preserving channel, then the decrease of variance, of relative variance, gives me a lower bound on the decrease of relative entropy. So in a sense, reducing the relative variance and the kind of fluctuations that it measures in a transition necessitates a proportional decrease in relative entropy as well. So that's the kind of results that we're studying in the paper. The nice thing about them is they're simple to evaluate, simple to prove. There are no hidden terms, no optimizations of the kind that you might have with min and max relative entropies. And other things that we have in the paper are, relating the relative variance to min and max relative entropy, bounding them, uniform continuity and subadditivity corrections. There's also an axiomatic characterization. And there's a bunch of applications that I hope you find interesting. So please go and check out the Google Blitz talk by Nelly if you're interested.
Okay, thank you. A quick question. When you say semi-classical in setting, what is that? Could you clarify that?
Yeah, I mean that both the initial and the final state commute with sigma. So they don't need to commute with another, but I want each of them to commute with sigma.
Okay, thanks. There's also a question from Mark, but maybe you guys can take it in Slack.
Cool, yeah, we'll do. Thanks, Mark.
Okay, next speaker. Seunghoan Song.
Hello, can you hear me?
Yes. Okay, go ahead.
Okay. Okay, thank you. So I'm Seunghoan Song from Nagoya University, and it is a joint work with Masahito Hayashi. And the title of this talk is Capacity of Quantum Private Information Retrieval with Colluding Servers. In this talk, I consider the private information retrieval problem. I call it the PIR in short. So it is a retrieval protocol without revealing which message is requested. So it is like this figure. So we consider a server contains F messages, and a user want to know the case message MK. In that case, for this purpose, the user sends some query and receives some answer. And at the end of the protocol, the server should know this MK, but the server shouldn't know which one is requested. So this K should be leaked, shouldn't be leaked to the server. So this protocol is called the PIR. And at first glance, it's very hard to find the solution of this problem, but there's a very simple solution of just downloading all messages. So by downloading all messages, the user can pick the targeted one, MK, but the server doesn't know which one is the targeted one. But this solution is very, very inefficient. And the efficiency of a protocol is evaluated by this PIR rate defined by size of MK over total download size. And so because this trivial solution has 1 over F, the rate 1 over F, so the rate is usually lower by 1 over F. And from its definition, it is less than 1. And unfortunately, it is proved that this trivial solution is optimal. So the optimal rate is 1 over F. So people try to find better solution with multi-server setting. So in the multi-server setting, we consider each server contains the same message set, and we also assume that they do not communicate with each other. So with this no communication assumption, the user secrecy is written like K is not leaked to each of the server. With this user secrecy condition, the PIR capacity have been considered only 4 years ago. And it is the optimal rate. So supreme of the rate is defined as a capacity, and it is derived as this value. So here N is the number of servers, and F is classical messages. And we extended in the last year's result this result to the quantum version. So in the last figure, the green ones are classical and the magenta is quantum. So we assume that the servers have classical messages and the user sends classical queries, but downloads quantum answers. And we also assume that the servers share some prior entanglement. And so we also consider another secrecy called the server secrecy. It means that the user only updates MK, but no other information in the server. And we derive the PIR capacity is exactly equal to 1. And in this work, we extended this result to the T private QPIR. So this T private QPIR is the same. This model is exactly the same as the previous model, but the only difference is that we allow some communication between the servers. So this problem considers MOT servers communicate to node K, but even in the case, this K shouldn't be leaked to the colluding servers. So we considered another secrecy called the user T secrecy, and we also consider this server secrecy. And we derive the T private QPR capacity is this value. It means that when the T, so less than half of servers collude, the capacity is equal to 1. So this good result of capacity 1 still applies even if some servers collude. And when more than half of servers collude, then this value is the capacity. So for proving this capacity, we constructed an optimal protocol with stabilizer formalism, and we also proved the converse bound. So this is a table of our quantum capacity and the classical capacity, and our result is greater than the classical ones. And if you're interested more, please come to my extended talk. Thank you very much.
Thank you. Is the collusion classical or quantum between the servers there?
It's a classical because we assume that the queries are classical, so they are in the colluding case they communicate classical information.
Okay, thank you.
Yeah, yeah.
Okay, the next talk will be Zahra.
Hello, do you hear me?
Yes.
Okay, do you see my slides as well?
Yes.
Okay, shall I start?
Go for it.
Okay, so I'm going to talk about quantum state redistribution for ensemble sources, which is a joint work with Andreas Winter in Barcelona. So we consider a source which comes from an ensemble, in contrary to the conventional quantum state redistribution, where the source is a purified source between the parties and a purifying reference system. Here we consider an ensemble. Here system A is the system that we want to compress. System C is the side information at the encoder. B is the side information at the decoder. And R and X are the classical quantum reference systems. We consider the asymptotic limit of many copies of this source shared between the parties. Okay, here is the exact task definition. So as you can see here, we have many copies of the source, which is shared between Alice, Bob, and a reference system. And the aim is that Alice wants to compress system A, send it to Bob via a noiseless quantum channel at rate Q. And then Bob wants to decode this state A hat N, and they aim to reconstruct the state at the end of the day and keep the correlations with this classical quantum reference system. And we also assume that they share unlimited entanglement in registers A0 and B0. As for the figure of merits, we consider block fidelity and per copy fidelity. For the block fidelity, we assume that the parties want to keep the fidelity for whole blocks of states, that is in n number of states, but with per copy fidelity, we consider that they want to preserve the fidelity for each copy. And also we can get per copy fidelity from block fidelity because we can trace out the systems, the rest of the systems, and we know that the fidelity is non-decreasing under partial trace. Since block fidelity is more stringent than per copy fidelity, we expect that to get bigger compression rates considering block fidelity compared to the per copy fidelity. So our rates are in terms of a function, a single letter function. So the function is Q epsilon, which is defined for this source state omega that I already introduced, and its purification. And here in the big omega, X prime is the register that purifies this state omega here. So this is the function that is going to appear in the rates. It might seem a little bit complicated, but I'm going to give insight behind it. So we know that for a purified state, that is conventional quantum state redistribution, the optimal rate is the 1/2 of the mutual information between the compressed system and the reference system. And here we have a similar thing, but since we are expecting to get smaller rates because we want to keep the correlations with the classical quantum reference system, we take the infimum over all this mutual information over all CPTP maps, which keep the fidelity for a single state source at least equal to 1 minus epsilon, because we are demanding less compared to the purified fidelity situation. And okay, so our result is that the optimal compression rate considering per copy fidelity is equal to the limit of the function at 0. Here Q0 is defined as the limit of the function at 0, and considering block fidelity, we obtain upper bounds and the lower bounds on the rate. The upper bound is the limit of is the value of the function at 0, and the lower bound is the limit of the function at 0. The problem is that we don't know this function, whether it is continuous at 0 or not, because this system Z, which appears in function Q of epsilon, can be potentially unbounded. That's the reason why we don't know whether it is continuous at 0 or not. But if it is continuous, then it is going to imply that QC star is going to be equal to QB star, and then they are both going to be equal to limit of the function at 0. And thank you.
Thank you. Next speaker is Yadong.
Hello? Can you hear me?
Yes, we can hear you.
Should I start now?
Yeah, go ahead.
Okay, thanks. I'm Yadong from Hong Kong University. This work is a joint work with Ge, Juliu, and Nana. I'm going to talk about efficient verification of continuous variable quantum states and the quantum devices when we don't have IID assumption. So given a quantum device, it outputs certain unknown multiplied quantum state rho m, and the verifier wants to decide whether needs to verify whether this output states is close to a tensor product of certain pure target states phi. In a more general general case, this quantum device outputs different quantum output states depending on the input state. And the verifier wants to determine whether this output state is always correct over all the possible inputs. Here, this quantum device doesn't have to work independently and identically in each round. We have two motivations for this non-IID setting. The first is in adversarial scenario, like verifiable blind quantum computing. This device may be controlled by an adversarial. The second motivation is in practical experiments, there may be time-dependent noise in the quantum device. We want to solve this problem by converting the non-IID problem into an IID problem. And we can use the definitive theorem for continuous variable quantum information. There are two known approaches. The first one is to, by doing some energy test, you can bound the dimension of the Hilbert space or mostly. Then you can apply the finite dimensional definitive theorem, but the approximation error exponentially increases with respect to D. The second approach is to use the so-called Gaussian definitive theorem. But the randomizing procedure here is expensive because you need to apply a random linear optical interferometer on your state. So here we propose our own alternative approach for our own purpose. It's based on finite dimensional definitive theorem. We employ both permutation symmetry and rotational symmetry on phase space. This permutation symmetry is easily achieved by randomly putting your subsystem in a random order. The rotational symmetry on phase space is achieved by applying random phase rotation at each mode. Then we use the finite dimensional definitive theorem, and the approximation error is quadratic with respect to D, which is preferable for verification of multi-mode entangled CV states. Then our protocol is to first apply dimension test to bound the dimension of the Hilbert space, then apply the fidelity test to check the fidelity of the state. This protocol can be used to verify any multi-mode Gaussian pure states and continuous variable hypergraph states, which is non-Gaussian. We can prove that our protocol satisfies both completeness and soundness requirements. It means that if the state is a correct state, almost certainly is flagged as a correct state. If the state is for false state, then we rarely give a false positive. This state verification approach can be extended to device verification by channel state duality. And our protocol, the sample complexity is efficient with respect to the number of modes. Yeah, that's all I want to present. Thanks.
Okay, thank you. Next speaker will be Supriyo.
Shall I start now?
Want to share your screen? Okay, go ahead.
Thanks to the organizers of Beyond IID in Information Theory for presenting my work, Elements of Generalized Salience Entropy in Classical Information Theory. This work is accepted yesterday in reviews in mathematical physics. And this is done with Professor Saiguru Furuichi and Professor Parthago. And I was a postdoctoral fellow at SN Bose National Center for Basic Science, Kolkata during this work. We know that the Shannon entropy is the simplest measure of uncertainty in a probability distribution. There are attempts to generalize the Shannon entropy, such as the Salish entropy, which use the Q deformed logarithm. Similarly, there are attempts to generalize the Shannon entropy with two parameters, such as the Sharma-Mittal entropy, Borgas-Doherty entropy, and this Scarfon entropy. Here also we propose a two-parameter generalized entropy. For this, we first introduce a two-parameter deformed logarithm, which I have mentioned in equation number 9, and we can prove that this log can satisfy the product rule of logarithms. Also, it follows the generalized log sum inequality like natural log and Q deformed log. Now we can define the generalized entropy in equation number 18, which is a generalization of Shannon entropy and Salish entropy. Like the Shannon entropy and Salish entropy, this also follows the non-negativity criteria. Also, we can prove a similar chain rule, which I have mentioned in equation number 21, and sub additive property, strongly sub additive property, and so on. We also define a two-parameter generalized divergence. We know that the Kullberg-Leibler divergence is most familiar one, and we can generalize it as a Salish divergence. We can also define a two-parameter deformed divergence like this in equation number 30. This divergence can also follow a few similar properties like Shannon and Kullberg-Leibler divergence and Salish divergence. Such as this is also non-negative. It follows the pseudo activity property like KL divergence and Salish divergence. It also follows the joint convexity property, and such things we can prove for this entropy also. For the detail of the proofs you may find in this article, and you may send your question and comments to my email address. Thank you.
Thank you. And there's also a question, and perhaps that question can be taken over chat on Zoom or on Slack. So the next speaker, Yuta, if you want to prepare your slides.
Okay. So, can you see the slide?
Yes. Yeah, go ahead.
Okay, thank you. So, thank you for coming to my lightning talk. So, the title of this talk is Third order asymptotics of variable length compression allowing errors. So, this is a joint work with my supervisor, Vincent Tan. So this talk is fully classical information theory, so not quantum information theory. So as you know, there are various classes of fixed variable length codes, and the most well-known class will be the prefix-free code. So in this code, any code cannot be the prefix of other codes, but we do not impose this prefix-free constraint. And we can allow the duplicated code words in our problems. So we allow error probability to be positive, but we restrict these are at most epsilon. So now we consider the discrete memory source. And this slide shows a very standard problem setting for the fixed length compression. And the bottom expression shows a very well-known results shown by the Strassen in 1962. So this third order asymptotic result in non-vanishing error probability regime is proven by the variation theorem. It is one of central limits theorem. And in this talk, we consider that this variable length compression. So the encoder maps the source symbols to the binary length, finite length binary strings. And we can use the empty sequence as well. So then the fundamental limit of this problem can be expressed in this asymptotic result. So this first order term is first proven by Koga and Yamamoto in 2005. And this second order term was shown by Kostina, Polyansky, and Bedu in 2015. And this third order term is our result of this talk. So now I talk about how I prove this result. And Bedu told in his channel lecture that the average codal length of variable length codes can be expressed by the fundamental limit of fixed length compression. And this equation is a minor extension of the Szymankowski and Bedu's result. So it's to evaluate the left-hand side, it suffices to calculate the integral of the fundamental limit of fixed length compression. But if we estimate this log of m star by variation theorem or the Edgeworth expansion, it's insufficient to obtain the third order asymptotics of this L star, because we want to consider the neighborhood of 1, but we cannot get a desired result because this central limit theorem gives only the non-vanishing error probabilities. So we derive this strong moderate deviation result for fixed length compression. So this, this S should be epsilon. So in this result, we can approach this epsilon to 0 or 1 polynomially first. So we can calculate this integral this result is this strong modulation deviation result is proven by the Kramer type large deviations.
Thank you.
So
So we have to move
oh,
on.
so sorry.
Yes.
Just I finished. Thank you.
Okay, thank you. Yuxiang is next.
Yeah. Okay, can you see my slides?
Yes.
All right, thanks, Eric, and thanks also for the opportunity to give you an overview of our recent results on representation matching, which is a protocol that reduces the communication costs of remote quantum computing. And this joint work with Masahito Hayashi. So the motivation of this work is actually comes from a quantum internet setting. Imagine in quantum network, remote users want to do computation tasks, want to fulfill computational tasks. And as a company that kind of provides service to those users, you may think of any possible way of reducing the communication costs of fulfilling such tasks. And then based on this motivation, we design a protocol that achieves this goal. So the concrete setting that we consider is as follows. So imagine that there are two users that are far away from each other, and Krista holds the state and arbitrary state psi, and David want to apply a quantum gate on Krista's state. And the task is for their local stations, station A and B, who provides the communication for David and Krista to fulfill these tasks. In the sense that at the end, Krista should hold the output gate, which has this UG target applied to her local state. And for security reason, Krista and David would not leak the information of the state and the gate to the stations. And the only information that the stations know is that the gate David wants to perform is an element from a group G. So this is actually the case for many real applications. And for instance, we often encounter like Pauli group and Clifford group and permutation groups. They all have group structures. So for these tasks, our protocol would apply. And our main result is actually twofold. The first result is that we propose the representation matching protocol, and the name representation matching comes from the fact that we actually make use of the irreducible decomposition of the group structure of David's gate into representations. And this protocol actually is a probabilistic protocol, and whenever it succeeded, it fulfilled the task with zero error and also capable of reducing the communication cost. And the second result is that we prove a generic lower bound on communication costs for any deterministic or probabilistic protocols in such scenario. And using this bound, we can actually show that our representation matching protocol is almost optimal in many real applications. For instance, you can consider the case of compression of unitary arrays where the target gate is actually parallel uses of a d-dimensional unitary. And as you can see from numerics here, the communication cost of representation matching, which is the right lines here, is obviously lower than a straightforward protocol where you don't use the representation matching. And it is also very close to the blue dashed line, which represents the minimum possible communication cost for any probabilistic or deterministic protocol, which is proven by our lower bounds. And besides, our protocol also works for other tasks. We have shown this for instance, for the storage and retrieval of quantum gates, also conjugation of unitaries, and also remote computation of other gates with other group structure like symmetric group. And you can find more details in our paper. Okay, I think that's it. Thanks for your attention.
Great, thank you. Thank you. Zixin is the next presenter.
Hello?
Hi, go for it.
Okay, cool. Hello, everyone. My name is Zixin, and I'll be telling you about quantum limited estimation of range and velocity. So the goal here is to estimate the range and velocity, or the separation in range of velocity of one or two targets. So typically, you would send electromagnetic pulses into the region of interest and examine the back reflecting signal to obtain these parameters. And the standard technique to resolve the target's range is based on the time of flight information, and its velocity can be deduced by the signal's Doppler shift. Now, the pulses have an uncertainty in frequency and time, and these are related by a Fourier transform. Traditionally, the energy-time uncertain relation puts a fundamental limit on the precision that you can measure these parameters. We have that the product of the bandwidth and its duration is lower bounded by a half. And we will show that entanglement can help lift this trade-off. So now we will calculate the ultimate precision in measuring the time of arrival and frequency of a pulse. The tool we're using is quantum estimation theory. If you want to estimate the ultimate precision of an estimation, you calculate the quantum Fisher information matrix. Now, the quantum Fisher information matrix is given by the trace of the density operator with the anti-commutator of the symmetric logarithmic derivatives. And the SLDs are defined like this. For its mnth element, you have the derivative of the density matrix with respect to the parameter sandwiched between its eigenvectors divided by the sum of the eigenvalues. Okay, so, and we calculate the quantum Fisher information matrix. And for the parameter time and central frequency, they look like this. So this is 4 times the bandwidth squared and 1 over the bandwidth squared. Now for a Gaussian pulse shape, the product achieves its minimum half. On the other hand, if we look at entangled state, the situation is something similar to quantum illumination. So you have something that's produced by SPDC pair. You send the signal towards the target and you perform a joint measurement between the signal and the idler. The QFI matrix now has an extra 1 minus kappa squared term on the bottom, where kappa describes the degree of correlation between the signal and the idler, and it's between 0 and 1. Now we see that the bandwidth duration product can now be less than half. However, we see that these two parameters cannot be estimated simultaneously, even in the presence of arbitrarily large entanglement, because the trace of this this commutation relation is not 0. So if it is 0, you can saturate the quantum Cramer-Rao bound. Okay, so now let's look at 2 targets. And the goal here is to estimate the separation in velocity and range. So the pulses might have a time and frequency profile like this. So traditionally, if the signals overlap, you would have trouble resolving this separation by using intensity measurements. But however, you can using a phase-sensitive measurement. So what we see in the quantum Fisher information matrix is that you have an analogous quantitative improvement when you use entanglement. But the interesting thing to look at is that for this commutation relation, this quantity actually approaches 0 for small separations, which means that in the case of small separations, you potentially can approach the quantum Cramer-Rao bound. And this is in contrast to the single target case where this commutation relation is constant. Now, this is counterintuitive, right? Because that's saying that the closer your objects are, the more likely you are to be able to estimate these 2 parameters simultaneously. Okay, and that's my last slide.
Great, thank you. And the last speaker is Samuel. And while he loads his slides, I just want to make an announcement to remind all speakers to please send your slides to beyondiid2020@gmail.com. Again, that's beyondiid2020@gmail.com. Thank you. Okay, go ahead, Sam, when you're ready.
Okay, great. So I'm presenting on behalf of myself and another grad student at Stanford, John Source, and we're just showing a new way to get matrix conditions for saturation of the data processing inequality. So just let's take any smooth distinguishability measure that acts on two positive definite matrices and gives us some real number that characterizes how distinguishable those matrices are. Then we say that this measure obeys the data processing inequality if for any completely positive trace preserving map, then the following function is non-negative. So this is what we mean by the data processing inequality, which just means to say that distinguishability does not decrease, does not increase under the action of a channel. Now, what we want to do is investigate the conditions under which this inequality becomes an equality. And it relies on a fairly straightforward observation, which is just that if this function vanishes, then it is attaining its minimum. So whenever this distinguishability measure is smooth, we can make a statement about the fact that a function attaining its minimum implies its gradient must vanish. Now, a function on multiple real variables gives us a gradient which is an n-dimensional vector, and here the gradient of this function on matrices is just itself a matrix equation. And we can evaluate it using some careful application of the chain rule in the context of derivatives acting on matrix manifolds to get an equation like this. And so most of the technical content of our work is just on carefully defining how these derivatives work on functions of matrices and evaluating it specifically for a few particular distinguishability measures. So we kind of develop some of the tools needed just to make sense of this approach. So let me give you a couple examples. Then if we have this distinguishability measure be the relative entropy, we get a known result here, which I think was found already by Petz. If we take the sandwich-Rényi relative entropy, then we replicate a recent result from a number of authors who I believe are here at the conference, which is that when sandwich-Rényi relative entropy is preserved by the action of a channel on rho and sigma, then we get this equality here. And the interesting thing about this is we show this result from a very different approach, because this originally was shown using convexity properties of certain trace functionals. And what we're doing is just showing a different approach of getting that same result. Why do we care about these saturation conditions? Well, for example, with sandwich-Rényi relative entropy, this is an intermediate step on the way to Petz recoverability, which was nicely shown by this recent paper by Wang and Wilman. And so if we can find an alternative proof of the intermediate step, we have an alternative proof of recoverability for these sandwich-Rényi relative entropies, but also that may mean it's then easier to generalize to apply it to other quantities and find new recoverability results. So we have this one-way implication that I've argued for. Turns out that under not too complicated conditions, we actually get that this is an equivalence, that it goes both ways, which shouldn't be too hard because we're just getting a scalar equality from a matrix condition, and the hard thing is really to go that first direction. It also gives new results for alpha Z entropies as well as the Petz F divergence, which you can see in our paper. And we're hoping that maybe that'll help us to find recoverability for alpha Z entropies, which as far as I'm aware is not known whether what conditions for what ranges of alpha and Z that actually holds. We're also hoping that taking this approach may lead to some approximate recoverability results, and that this idea, straightforward as it is, may actually give new saturation conditions for many other inequalities. Thanks for listening.
Okay, thank you, Sam. And thank you to all the